Hello, Internet. We are live.
Hey everyone, welcome to episode 63 of the Stanford MLSys seminar series. I'm Curran, and as always, we have with us Dan,
Hey.
Hiro,
Hello.
Yudor,
Hello.
and our guest today, Arjun Akula from
And
Google. So, as always, we're going to have a 30-minute talk followed by a 30-minute podcast style discussion where you, the live audience, can send in questions. You can keep those questions coming during the talk, and we'll get those across to Arjun at the end of the talk. A little bit about our speaker today. So Arjun is a research scientist at Google AI in the Mountain View office. He got his PhD from UCLA, and he works on computer vision, natural language processing, and deep learning more broadly. I believe today he's going to be telling us about some of his work around improving robustness and interpretability in vision and language grounding models. So Arjun, take it away.
Yeah, thanks so much, Karan. And first of all, thanks so much, MLSys team, for inviting me. And for everyone for tuning in live on YouTube. Hi, everyone. I'm Arjun. As Karan mentioned, I'm a research scientist at Google. So let's get started. So I think Karan already covered a little bit about me. So I got my PhD from UCLA. I worked with Google, Amazon, and Mila during my PhD. And I also have worked a little bit for about 2.5 years at IBM Research before I joined my PhD. And I got my bachelor's and master's from Tripathi, Hyderabad in India. Now, so today's topic is about robustness aspects in vision and language grounding. This is what pretty much what I've been doing as part of my PhD work. So even before I get there, let's look at what is exactly vision and language grounding, because I think the notion of grounding is like not very familiar with for researchers who are not into this multimodal space. So I'll quickly start with a quick definition of grounding. So by grounding, essentially we mean relating abstract language symbols to objects and actions in images, or it can be videos or any other perceptual experiences. As a quick example, let's say you have a natural language expression, something like this. Place the package at the destination in front of the door to the right of the elevator, and say a drone is actually trying to deliver the package based on this given instruction. So for the drone to correctly deliver this package, it really needs to understand this spatial relationship, such as in front of, to the right of. Also, what does it mean by package? Where is the elevator? So trying to relate these symbols mentioned in the language expression and trying to map it to objects in the image. So roughly, this is what we call as grounding here, trying to relate these symbols in the image. Now, so why is grounding very important? So grounding establishes a communication channel between humans, machines, and the physical world. And you can see there could be lots of applications, be it a video recommendation, video retrieval, or autonomous delivery, the example I just showed you, and also, of course, chatbot-based applications. So this is all good. So now we understood the what is language grounding. Now we touch a particular aspect of this, like how do we evaluate? Let's say you have these vision and language grounding models. How do you evaluate how robust are they in terms of adapting to new samples that were not seen in trained data set and things like that? So even before I get there, so let's take a quick look at what I mean by robustness here. So you might have seen this popular works, for example, from ICLR 2014, where there is this notion of adversarial attacks. Within an image classification framework, you add some noise that for a human eye, it's not actually visible, but if you actually give this modified image to the image classifier, it actually gets the gives you a different classification. For example, a bus changing to ostrich. So also there are other very interesting works like I think in the context of face recognition, where wearing a these frames can actually change the classification decision. Like so, basically the idea here is like they kind of attach some sort of patterns on top of this, the lenses, and that would basically trigger this models decision. Now, coming to the multimodal setup, like the vision and image, or vision audio, or vision language navigation. So there are a lot of multimodal setup problems with this, and so if you take visual question answering, for example. So this is an example I often cite in my work. So this is the actual confidence score that I got by running a VQA model. So if you ask a VQA model a question like, is there a beach, given this image, it says yes, with a very high confidence score, like about 87%. And if you again ask a follow-up question, is there a surfboard? Again, it says yes, with a very high confidence score. But see, the first one, it actually makes sense. I mean, it's right, and there's indeed a beach, but it's really hard to see that there is a surfboard or not in this image. So it's basically trying to get this decision by using some sort of biases, right? So given it's a beach, so it's kind of thinking that maybe there's a high probability for a surfboard. So it could be right, it could be wrong, but it's clearly not justified decision. So that's the reason why we really need to understand the robustness aspects. It essentially helps us in understanding, what we want. Basically, we want to know what the model doesn't know. And in addition to that, it also helps increasing and quantifying the human machine trust. Because starting from CNN, we have seen all sorts of new models coming in, like transformer to multimodal transformers to clip, YOLO. So given that these models are doing so well, so I think it's the right time to really understand how well do they, perform on like unseen samples, which not necessarily follow the same distribution that the model is trained for. So that's a little bit of motivation as to why the robustness evaluation is important. So let's try to see what are different ways we can get a sense of this robustness in some of these models. So I would class, although there are like multiple works across this dimension, at a very high level, I see like there are three important ways to try to understand this robustness. So one is through explanations. So explainable AI frameworks, they try to they help you understand like what are the cases where the model actually fails to do correctly, and what are the cases where the model can actually do well. And the other approach, popular approach, is through adversarial analysis. I'll talk about that in a bit. So, and also, of course, distribution shifts. Given that vision and language is a multimodal problem, how do you do this distribution shifts? For example, in language versus distribution shifts in image space versus distribution shifts in both image and language space. So I'll try to give a example in each of these three different directions. So let's start with the first work. So this is one of the work that I published in AAAI 2020, where I try to propose something called counterfactual explanations with the aim of trying to understand what are the cases where, examples where the model tends to do well, and where the model kind of just goes with a random decision without really trying to understand the input. So this work is done in the context of image classification. Let's say you have a training data set of different images and their classification categories like Taylor Singh, dog, frog, goat, sheep, and you train a simple CNN model to try to classify these categories into one of these predefined set of classes. Now, coming to the inference side, so let's say you input a new image during inference, and your model comes up with this decision that the input image is dog. And so, but now what we want to do is we want to understand, at least want to see what are the most influential factors that the model is looking while making this decision down. So for that, we ask a counterfactual question to the model. like what changes I need to do in the input image in order to change the model's decision from dog to thylacine. So this is what we call it as alternate class, and this is the predicted class. And our framework can actually give you that the model is, I mean, if you want to change the model's decision from dog to thylacine, one of the highly important features that you want to add in the input image is the stripes, because that's usually what kind of differentiates between a dog and thylacine. Similarly, what are the features that you want to take out from the input image in order to modify the classification decision from taught to frog? Sometimes you want to add some things and we have to take out, remove some things from the image in order to trigger this decision. For example, goat to sheep. So these kind of frameworks will help you, at least at a high level, help you to understand, what are the key influential attributes or factors that the model is looking into, and you can take more informed decision in real life applications. Like, okay, maybe so once you get a sense of where the model gets to do well, where the model fails to do well, then you can better use these AI tools. Coming to the second dimension, as I mentioned, so adversarial analysis is another way to to get a sense of how robust are these models. Now let me just to give a better picture of what I mean by adversarial analysis here. Let me introduce a task, and then I'll go over some of the robustness issues. So in this case, I'm taking a task called grounding visual reasoning expressions. Essentially, the task here is given an image and its bounding boxes. Bounding boxes essentially refers to the objects that are present in the image, and also a natural language expression, something like the zero facing the tallest zero. Now, the goal of this problem is to identify what is the target bounding box that this expression is referring to in the input image. So that's the kind of task setting. So it's clearly a multimodal problem involving image and also the language dimensions. Now, so when we actually ran all the state-of-the-art models on this particular task, so for example, ViLBERT, which is a multimodal transformer, which it comes almost close to 84%. Whereas the human performance on this task is around 86%. So clearly, these models came almost close to the human level performance, and it casts doubt. Like, is it really the case? I mean, are these models are as good as humans in terms of grounding this target object? So in this paper, we actually show the answer is no. And the reason why these models do so well, like come closer to human level performance, is because they try to exploit some sort of reasoning shortcuts in training. And because by leveraging those reasoning shortcuts, they try to crack the test set, but that doesn't necessarily mean they're able to get the semantics correct. And so given this problem, so let's diagnose the robustness aspects here through adversarial analysis. So for this, what we did is we collected this adversarial data set. For example, this is the original language expression, the zero facing the tallest zero, and this is the correct bounding box that this language expression is referring to. Now we collect another adversarial counter sample for this through human annotation, where we ask them to provide, write a new expression with minimal edits to the original expression, but actually that changes the target bounding box. So in this case, the bounding box shown in red changes to something highlighted here. And you can see the difference between the two expressions. Here it's saying the zero facing the tallest zero versus the zero facing away from the tallest zero. So looks like both looks like pretty much same, but only if the model is robust enough to handle the spatial relationships like facing versus facing away, the model can get right on both these samples. Otherwise, model will be able to do well on one of them and it will fail to do well on the other side. So that's the idea of adversarial analysis, and it will immediately tell you how robust are these models in terms of grounding the language expression. I see a question coming up in the chat. Let me.
Don't worry about the questions right now. We'll get them to you.
Oh, okay. Oh, perfect. Yeah, sure. So let's move on. So as part of this stuff, I also want to, so given that, let's say, so I mentioned that adversarial analysis still, give a sense of whether these models are robust or not. Okay, let's say you found these models are not robust. What are some ways you can fix this problem, right? Because that's also very important, especially in the context of industrial applications. So I'm going to give one such technique, which actually worked really pretty well in our case. So it's basically the multitask learning, which is pretty popular, but also very powerful technique, I would say, in terms of improving the robustness. And so we did multitask learning with something called GQA from Stanford. So GQA is a question answering data set, which tend to have lots of spatial relationships in its questions. And that's the reason why we wanted to perform a multitask learning with this data set, because our original referring expression recognition task also involves grounding lots of spatial relationships like in front of, or behind or above, this kind of spatial relationships. So we thought performing multitask learning alongside GQA would kind of help in increasing the model sensitivity to to this linguistic structure. And so we did see actually pretty good improvements. I'll come to that in a minute. But before that, I'll also maybe briefly explain how we conduct this multitask learning. So we start with ViLBERT, which was the best performing model when we're working on this particular problem. So ViLBERT, to give a bit of context, it's a multimodal transformer with trained using two pre-training objectives. One is masked multimodal learning, and the other one is multimodal alignment prediction, which is pretty similar to what we have in BERT, right? So in BERT, we have this masked language modeling and also something called next sentence prediction. So in this case, it's more like a image text alignment instead of the next sentence prediction. And the ViLBERT is trained on like about, I think, 3 million conceptual image captioning pairs. And once after the pre-training phase, this is how we pass the inputs to ViLBERT. So the input bounding boxes in the image so we first extract them and also we tokenize the text. Now the bounding boxes are passed through the visual transformer layers, and the expression tokens are passed via language transformer layers. And then we have this co-attention transformer layers, essentially to perform, image conditioned language attention and language conditioned image attention. And finally, at the end, we take a element-wise product of image and language presentation, and then pass this, the final embedding to task-specific layers. So one, as I mentioned, we use the GQA task, and we do a multitask learning alongside the referring expression recognition task. So basically, we pass a batch of samples for GQA, compute the loss, and backpropagate the gradients through the shared layers. And then in the next round, we pass the samples from referring expression recognition, again, compute the loss and backpropagate the gradients. So we do this alternate training kind of a style there. And then we saw pretty good improvements over the pre-existing ViLBERT model. And so to get more detailed analysis and to get more detailed results, you can go through this work published in ACL 2020. I'll move on to the third direction of evaluating robustness. It's through the distribution shifts. It's actually pretty new, I would say. We are like in some of the initial researchers who started looking into this direction. So what I mean by distribution shifts, let me take the task of visual question answering, and then I can explain what essentially I mean by distribution shifts here. So as most of you might be familiar with this task of visual question answering, where you have these questions: who is wearing glasses? And from an image, you need to answer. So Here the man is wearing the glasses, here the woman is wearing the glasses. And other questions like, is the umbrella upside down? Yes or no type of questions. So these are the questions I got from VQA 2.0 dataset. Similarly, there is another dataset called ViLBERT, which also has this question answering page. So if you look at the images and its questions, does this foundation have any sunscreen? Yes. Similarly, what type of soup is this? Unsuitable image. So you can always say, like, if you cannot find the correct answer from the image, it's allowed to say unsuitable image. Now that you have seen examples from these two different question answering data sets, you might have observed some differences, right? Basically, VQA 2.0 is built on top of high quality and cleaner COCO images, whereas ViLBERT, on the other hand, is collected in the wild from visually impaired users with low. That's the reason why it tends to have a low quality image, and also the question styles tend to be more conversational and simpler compared to the questions in VQA 2.0. So clearly, the point I wanted to bring up here is clearly there are distributional differences in terms of image space and also the kind of questions that we have between these two VQA data sets. Now, the question that I would like to pose here is, let's say you trained a VQA model on VQA 2.0 dataset, and now you want to adapt it to ViLBERT. How do you evaluate the adaptation skills? Similarly, if you train a model on ViLBERT dataset, and to what extent can we understand how well it can adapt to the samples from VQA 2.0? You could say, why not just on the test sets, right? So let's try. You can train a model on VQA 2.0 and you can test it on ViLBERT. But that can only give you a very high level understanding, but it doesn't give you any detailed insights as to what went wrong. For example, if the model couldn't adapt to ViLBERT, it could be because of distributional differences in the language space, or distribution mismatch in image space, or it could be because of distributional mismatch between both image and language space. You cannot draw all these detailed insights using existing test sets. So that's one question we had. And another limitation is, so today, if you have a VQA model, you cannot evaluate the adaptation capability of this model on a non-VQA data set. For example, open images, it only has image annotations, but it doesn't have any question answer page. So how do you go about evaluating in the wild performance of your VQA model on these open images kind of samples? So that's where we actually come in and say that, hey, so why not use a VQG kind of a model to generate all these different types of distributional mismatch test sets. For example, so we propose a VQAG model that can actually generate a VQA2 style question answer pair for a VQA2 image, as well as a ViLBERT style question answer pair for a VQA2 image. Similarly, you can generate a VQA2 style question answer pair for ViLBERT image, and of course, ViLBERT style question answer pair for ViLBERT image. So see, immediately you have all this, mismatched image and language pairs. And if you go and evaluate your model performance on all these different scripts that are generated by this language generation model, you will immediately know what went wrong. So is it because of language mismatch, or is it because of mismatch in the image space and so on? And also, how do we actually go about implementing this VQAG at a high level? I'm not going to talk too much into the details, but at a high level, we have two phases, the training phase and inference phase. So VQAG is basically, we use a transformer, encoder decoder transformer model. The model uses a dataset indicator to learn and generate question answer pairs of a particular dataset style. And during inference, we apply the trained VQAG model to multiple image sources denoted by A, B, and C. For example, A could be VQA2, B could be ViLBERT, and C could be open images. And the trick here is like while doing this inference, we kind of change the dataset indicator. So for an image selected from A's domain, we provide the indicator B. So that's how we were able to generate this mismatched questionnaire language. And this is the detailed architecture. So at a high level, as I mentioned, it's a simple encoder decoder model, but there are a lot of engineering tricks, I would say, to be able to really get it right. So we were able to we found that conditioning it on, for example, semantic object labels of the image and the question category that you want to generate, and also the prefix of the question that you want to generate, it would really help in generating very relevant question answer page. And you can find more analysis in our paper. And here are some examples that were generated by our model. So here, for the VQA2 image, this is a question and answer that is generated by our model, which is of style VQA2. The reason why we generated this VQA2 style image and questions is just to make sure that we were able to generate questions that look similar to what we have in the ground truth. And but what we are really interested in these type of questions, right? So given an image of from this list, can you generate question and answers from VQA2 style image dataset? Similarly, given an image from VQA2 dataset, can you generate question answers from like that looks like a VSWIS style of question? And there's a lot more analysis that we do there. I think we have another 5 minutes, I guess. So let me quickly conclude this. So basically, what I did today is giving a very high level, directions as to what are the ways in which we can evaluate the robustness aspects in some of these vision and language grounding models. I've shown that explanation is one direction, and adversarial analysis is another direction, and distribution shifts is a new direction that you can go with to perform this analysis. And I would say these insights that I have shown here, and also some of the analysis that we show in our paper, can be generalizable to other multimodal, settings like vision and audio, or vision, language, and navigation, and so on. And so coming to the future work, or some of the work that I have been doing, after my PhD, and also at Google here, is trying to also evaluate the systematic compositionality and generalization aspects of some of these models. For example, how can we build compositional models, which is very important problem, which has not been addressed so far. So there are some works recently, along this direction, but there's a lot of room there to be able to make progress, and also the continual learning kind of a direction. So the last one that I presented here, the cross which way direction, is kind of a continual learning kind of a framework where we kind of avoid the human annotation cost there. Rather, we automatically go about collecting these dynamic benchmarks, or you can call it contrast sets or test sets. So that's another pretty interesting direction I'm looking into these days. And of course, common sense reasoning capabilities. How can you incorporate these capabilities? Although we have these data sets to evaluate this, like visual common sense reasoning test sets, but there's still a lot of room over there to improve performance of these models. And finally, how can we come up with robust representation learning? It could be either through pre-training objectives, or it could be either through the actual modeling stage. But having access to this robust representation learning, again, is a pretty interesting direction. So with that, maybe I would stop here and see if there are any quick questions.
Awesome. Thank you so much, Arjun, for the great talk and covering so much ground as well. I want to remind everybody who's in the YouTube audience, as well as in our Stanford class, that you can send in your questions either on YouTube chat or in the chat on Zoom webinar, and we'll get those across to Arjun. So I guess to kick things off, I had a question, maybe a little bit about the generation work, and specifically the types of questions that get generated when you do the VQAG work. I guess when I was, when you were talking about it, I was almost wondering if generating questions given an image is is it any easier than answering a question and image pair, basically, because like in some sense you have to know all the objects, you have to know the grounding in order to be able to generate a reasonable question that is also hard enough that it would be an interesting question. So I'm just wondering if you've evaluated that aspect of the generation to understand, are the questions interesting in some way comparing to the original data sets. It seems like the style matches, but does the sort of difficulty also line up, and does the kind of do the questions make sense? Are there errors sometimes that you see? I'm sure there are, but just curious about kind of the characteristics there.
Yeah, that's a pretty good question. So we do actually a lot of detailed analysis on the kind of questions that we generated. So I think one of the first questions that you put here is, was it any harder or simpler compared to just taking an image and a question as input and just predicting the answer? Yes, definitely. Generation is relatively like much difficult. I would say the difficulty is not about generating a question, but if you see there, we are generating question as well as the answer for the question. So getting the correct answer is very difficult there, because our success rate was about like 55% when we did this. So we actually sent it to human annotators inside Google, and they actually tell us whether the question is relevant for the input image and whether the generated answer is, whether it's correct or not. If it is incorrect, they actually go about and annotating new correct answers. So that's how we clean the data set. And question relevance, coming to the statistics, the question relevance was like pretty high. Of course, we didn't get it in the first shot. As I mentioned, there is a lot of engineering effort, I would say, especially in terms of what kind of signals that you want to provide on the encoder side while you train this architecture. But after we incorporate all these different types of control signals, the question relevance was about almost like 98%, which is pretty good. And the answer correctness, as I mentioned, it's not good. There's a lot of room for improvement over there. So we got only like 54% of the generated answers were correct. And coming to the third part of your question, any other statistics that we did, in terms of analyzing how interesting is this question, right? So that's where we kind of introduced new metrics as well, because of course the automatic metrics like blue score or cider score, they only check like whether the fluency of the generated questions, but not so much on the semantic aspects, right? So we introduced something like novelty of the question, because if you are really not very careful in training these models are smart enough to just copy paste an image question from training set and just it would appear as if it is generating a new question, but under the hood it's just actually copy pasting the question from train set and generating. So to avoid those kind of scenarios, we had this metric called novelty and inventiveness, like compared to the questions that we have in training data, how inventive is this new question that we got in the test set, and also of course the novelty and diversity kind of aspects, and a lot of other things that we evaluated in the paper. Yeah.
Okay, yeah, no, that was a great answer, and I think I think just a quick follow-up in terms of like the novelty and stuff. Do you actually, like, I imagine it's not easy to evaluate that automatically, so you must have either some rule-based thing or somehow use humans to do it. So I'm just wondering, is it automated, or is it something where you have to send it to a human to say?
Yeah, so I think the novelty part comes here in the context of zero-shot classification kind of a setting. Basically, so in the actual VQA 2.0 dataset, for example, there is only class fish, but there is no mention of a class called shark. But in the test set, you were able to actually generate a question with shark as like the word object shark mentioned in the question. But you would be wondering like, how is it even possible, right? So that's where the pre-training actually helps. So we pre-train our model on 17 million conceptual captions data set, which is published in CVPR 2022. So that's where we try to kind of, get this zero shot kind of, because in the fine tuning phase, it never saw these objects, but during the test time, it is able to create new questions using this new kind of object phase. So coming to your question, do we have any rule-based rule-based methods to get this novelty score? Yes. Basically, we saw like how many new objects that were not available in the VQA2 or VSWIS dataset, but actually the model was able to generate in that test. So we did.
Okay, that's super cool. Yeah, that is pretty interesting, actually. Thank you so much. Yeah, thanks for that.
I actually have a small follow-up on this because I'm really curious about that, Arjun. From the same image, one could ideally generate a potentially infinite amount of questions, right?
Yep.
I'm very curious about the, if you took a look at the variety within the possible generated things from within the same images, and there's any characterization there, and is anything that is worth discussing about it?
Yes. So it is possible that you can generate any number of questions, but actually in our experiment, so if you don't provide any signals on the input side, let's say you only give an image, and because this is an encoder decoder setup, so you have to fix, so you use this Bing search, right, on the decoding side, where you have to set the number of type of questions that you want to generate. For example, Bing size of 5, then you would get like 5 different types of questions on the decoded side. But the thing is, these questions are all tend to be similar. We didn't see any like huge difference in these questions. So that's where we thought, let's try to add some sort of triggers on the encoding side. For example, I want to generate a question starting with is there. So then it's able to generate a question starting with is there. And again, we ask the model to generate a new question for the same image, starting with the prefix what is. So then it's able to generate a new question. So that's how. So we had these 16 different types of varieties on the the prefixes that we put, provide on the input side, and that's how we were able to actually increase the diversity on this generated question. So yeah. So I think that's one thing we did to make sure that model is not generating the same question, as well as to increase the diversity of this question.
Right. That's interesting. It makes a lot of sense. Yeah. Thank you very much for the answer.
Arjun, one of the things that I was curious about when I was kind of listening to the presentation, I wonder, is there any role for kind of logical primitives or like kind of physical primitives in your training system, or how you think of those? That first example you gave with the robot that needs to place a box kind of left of a door, you can imagine maybe in the olden days of doing computer vision or things like this, you might have a bunch of rules that have to, left means that the X coordinate is less than something else. I wonder, do you guys try to incorporate any of that sort of logical reasoning into your training system, or is there any way to like kind of incorporate these things that you kind of know about, but you don't necessarily have a way of, I can't point to the left of node in my neural network?
Yeah, I think this is a pretty interesting direction. I think, so I did work a little bit on something called neuro-symbolic AI kind of a direction, where you have some sort of flexibility in incorporating some of these logical constraints into the model. But for the works that I presented today, actually, the answer is no. So we didn't add any of these logical constraints. But I also worked a little bit on something called neural module networks, where you can actually can provide, because if you are familiar with neural module networks, you basically have a set of different neural modules, like smaller neural modules, which were dynamically assembled during the inference time. And each module has some sort of semantic nature associated with it. For example, one neural module, it always does this operation of filtering an object by shape. And the other neural module, it always has this operation, it always does this operation of comparing two objects. So if you have some sort of semantics, label for these smaller atomic neural units, then it would be possible to add, these constraints. so I would say neuro-symbolic AI is really the direction to go in order to incorporate some of these logical constraints or the physical constraints. And coming to, I think it also reminds me of another direction. So I also work in this space of vision language navigation. So there you don't really have the real robot, but you have a simulator where the robot still needs to, you have this task for the robot to, you call it agent basically because it's an embodied AI kind of a setup. You give some sort of instructions like go to the kitchen, open the fridge, take out the letters out, and cut the or take out an apple out, cut the apple into pieces, so slices and all. So there, still it's not physical constraints, but there are some sort of constraints embedded there because you cannot cut a plate, right? You can only cut an apple. So there are some semantic constraints, embedded into that framework. Yeah, so that's another work I remember, where this kind of constraints were, are actually incorporated into the model architecture.
Gotcha. Do you think the field is kind of moving towards or away from this constraint-based like way of thinking?
I think I would say so. Vision and language is already old. I would say the latest hot direction in this space is vision, language, and navigation because everyone is moving into this direction. All the people I think pretty much I knew who were in vision and language space a couple of years back, they all like started working into this vision, language, and navigation all of a sudden. So because it's even more challenging because it's not just about understanding image and text. It's about understanding that in a context of a room, like where the robot also needs to navigate to a specific location, and you don't have a simple language sentence there. You have a series of instructions to comprehend. So that makes the task more interesting and more challenging. And yeah, I think there's a lot of interest in that particular direction now. And yeah, I hope there is the field will be moving super fast, given that a lot of researchers are into this space right now.
Gotcha. Yeah, that sounds really interesting. Definitely seems, interesting to add that extra bit of that real world interaction, that navigation into the components. One thing, another kind of maybe random thought that I had was, do you guys ever think about maybe intermediate representations when you're thinking about these things? Like something that I thought of just very briefly would be, we've seen that like the GPT-3 style things can generate code very easily with GitHub Copilot. Do you think maybe there will be a Python module inside of your network that just like generates some logic that can maybe do some logic that's easy to express in one sense, but maybe not so easy to express in just kind of training end to end?
I think so my PhD, so I was working on this grant called DARPA Explainable AI grant. I would say this entire field of explainable AI is all about that. So you have this end-to-end model architectures doing pretty well on most of the tasks, but you have no way of understanding how exactly to infer this problem. Like, does it really understood the color of the object? Does it really understood the size of the object? So I think but the thing is, if you want to see all these representations explicitly, there are a couple of ways to do that, but the model performance was unfortunately not at all good. So that's why people, I think most of the time they end up following this end-to-end architectures. But a nice combination, nice fusion of getting some sort of interpretability advantages and as well as getting this end-to-end representation learning advantages would be, as I mentioned, the neuro-symbolic AI would be the way to go to be able to get that. So I did work a little bit, as I mentioned, on the neural model networks, which is one of the framework in neural symbolic AI kind of a setting. Cool. There you can actually see that if let's say to take this visual question answering task. So if the model set is how many people are in the image, let's say the model gives you the answer as 2, you can actually see how the model came up with this answer 2. You can see that as a tree, hierarchical tree, like similar to the syntax tree in language or dependency tree in the language, you can see like, okay, at the leaf level, the model tried to understood the color, the model tried to detect the person. Then based on that evidence, it tried to perform more aggregate operations in the second level. And finally, it is able to reach this decision that there are two people in the image. So that's a kind of pretty good intermediate representation these neural model networks would give you. But unfortunately, transformer-based models, they outbeat these models. So no one is very interested to explore more into this direction. So we got a paper along that direction in URIPS last year, which tried to address some of the robustness issues in neural model networks.
Cool. Always great to hear Transformers eating up more research projects.
I wanted to kind of follow up on this idea of adding kind of more logic and semantics to the pipeline of ML that tries to kind of, reason about what's happening in an image or video clip. It seems like a large part of being robust in this setting is, being able to perceive and understand enough of the context in order to disambiguate what's going on, right? So in the example you gave with that train on a beach, if I squint, the shadow and the train kind of make a surfboard-like shape, right? So I can understand why a single model that's just trained to detect surfboards might get confused. But if we want to be robust in this setting, we need to have a model that is capable of reasoning about what is in that general area, and if that model can say, I have much more confidence in a train being in that part of the image, that would then, with some semantic kind of or logical rules, would rule out there being a surfboard in the same area, right? So it seems like not to mention, and I think this is what I really wanted to talk to you about, is the extensibility of this kind of approach, right? Do I really want a specific model that's trained end to end on a single task, or is it a little bit maybe more advantageous to have a set of models, kind of like in the AV space, that first reasons about, okay, show me, detect as many objects as you can in this image, and then if I care about the people in this image and maybe what they're wearing, I can focus on that part. But that's another set of models that does that and answers those specific questions, right? But I can take pieces of that model and use it to reconstruct an entirely different kind of end-to-end pipeline.
Yeah.
So maybe you can comment on kind of the extensibility of these approaches.
Yeah. So that's a pretty good point that you mentioned. Also, it reminds me of another example that I used to give as part of I think when I was in the third year or fourth year of my PhD. So I think the VK models are now a little bit more smarter than what they were like a couple of years ago. So when I used to play with this VK model, so there's only one person in the image. And so if I ask the question, is there a man in the image? The model is to say yes with 96% confidence that it's yes. And if I ask a question, is there a woman in the image? Again, it says yes with a 96% confidence. So it doesn't have any sort of logical or some sort of common sense logical understanding that if there is a man, then there can't be a woman in the image, given that there's only one person in the image. So clearly, these models lack that level of common sense, constraints that we as a humans are very good at. What you said might be a direction, like you can do some sort of compositional modeling where you have different set of models trying to understand different aspects coming from the image, and then you can kind of aggregate the analysis from each of them. For example, you can have a model to just detect a person is in the image or not. You can have a model just to detect whether there is train in the image or not. And then if there are some questions asked about in general understanding of the image, then dynamically you can try to aggregate these smaller level detection modules to draw the detailed inference. Again, that is what the neural model networks are invented for. But the thing is, they don't do well. So this is all very good, but the problem is they do. I mean, they used to do well before to the transformers era, but once the transformers are coming to the picture, especially with this vision transformers and the clip kind of pre-training objectives, it's really hard to compete with them. I mean, yeah, so we have to deal with that. I mean, basically we are kind of ignoring the interpretability aspects by keeping the performance, by giving more priority to the performance aspects. So some people actually argue that if I'm getting a very high performance, why do I even bother about interpretability? Makes sense, why not? But some people might, like there could be some sensitive domains, let's say like medical diagnosis. Let's say if the model is trained to detect whether you have a cancer or not, then interpretability might be very important, because even if you have 99% accurate model, that is not going to be enough. So their interpretability might be more important to make more informed decisions. So yeah.
I think an interesting corollary here, though, is how and where in the data distribution these models perform better, right? And in particular, transformer models perform better, because if you think about the the world as a big distribution, and if you consider just one relationship, if I remember, I was working in grounded language understanding a little bit several years ago, actually, like 6 or 7 years ago, and in one that is that we were using back then was called visual genome, and in visual genome, if you just took the relationship left off or right off, you would see that for like really frequent classes like humans and some types of animals, you will have like almost an even split of humans occurring with humans left off, right off, or humans occurring with dogs right off, left off. But if you go to the tail of distribution, like I remember one specific interesting example where there were 6 bears and cars. Bears occurred 6 times on the right of a car and 0 times on the left of a car. So if you train on that kind of data, obviously the model will never learn, and you don't have any prior or inductive bias. The model will never learn that bears can occur on the left of a car, because there's not even a single example, right? And so when you test a model, if you test on like the same distribution from the data, so it's very sparse and very long-tailed, obviously the capacity of the model will be concentrated on working on the fat part of the tail. But so in that work that we did a while ago, we were actually changing the distribution and making it like completely uniform. And if you tested on the uniform distribution, meaning now I also care a lot about bears and cars as much as I care about humans and dogs, then in those cases, models without inductive biases will perform substantially worse. So I'm actually curious if a neural model network approach would actually work really well in the long tail rather than in the fat part of the tail. What do you think?
Yeah, I think that's again a pretty good point. I may not be able to say whether I think these models would be able to do well, let's say on the heavy tail versus the long tail. But definitely, so previously, like before this pre-training kind of an objectives coming to the picture, these models definitely they weren't not able to do so well on the long tail, objects or classes in the image. For example, you mentioned if there is no object mentioned or that is mentioned very less frequently in your training set, then the model may not be able to handle them correctly.
So simply training helps there, right?
Yeah, the pre-training can actually help there. So that's what we saw. Like pre-training is a way to kind of combat those issues because typically you pre-train with like millions of at Google, I think we have this like 400 million or even something billion data sets. Then it's kind of very, at least I would say, not so easy to miss out an object or class, given that you're covering like pretty much the entire space, entire like space of this object. So with pre-training objectives, I would say that may not be a problem, but it used to be a huge problem before these pre-training kind of objectives were actually coming to the picture. Yeah, so that's what I observed in my.
No, it's very interesting. I think the space is evolving in a direction that is interesting. So thank you.
All right, yeah, I think we're exactly at time, so that was a great discussion, I think. Thanks to you, Arjun, for joining us in this part of the talk and talking to us on YouTube. Thanks to everybody on YouTube who tuned in or is going to watch, after the video is posted, which will be right as it ends. As always, go to our website, mlsys.stanford.edu, sign up to our mailing list and subscribe to the YouTube channel. We don't spam too much. We only send a couple of emails a week to tell you what the talk is. So please watch out for those emails if you are subscribed to the mailing list. And I believe we also have podcast up. So we put these up on all the standard podcast places, Spotify, Apple, Google also. Yes. Okay, great. Yeah, Dan's giving me a thumbs up. Yeah, so check those out. And next week, we're going to have folks talk about how Uber predicts arrival times using deep learning. So that should be fun. See you all next week. Bye, YouTube.
Bye.